we are almost coming to end, means almost 3 days were completed, and now we are going to start the 4th day, so that the days are going very fast. So this during today, so we are going to have first session on the 3D printing processes 2. As I mentioned, with a little deviation in the title of the topic, I could not put it in that material wise, the classification, because of the developments in the 3D printing technologies. So I have made it to the 3D printing processes sessions. So the one which yesterday we have covered 4 kinds of, as we know that this is the 7 categories that the recently ASTM has classified these 3D printing processes into 7 groups. So which we have covered 4 processes yesterday. So that is during 3D printing process 1. So we have covered VAT photopolymerization process. So let me summarize, say what is a VAT system. So VAT system consists of a tank, which the raw material is in a liquid form, and the energy used here as either a laser energy or a LED or a LCD to cure the liquid photosensitive polymer into a solid one. So that is about a VAT photopolymerization process, which you have the materials right from the plastics and ceramics under this VAT photopolymerization process. Of course, metals also. So coming to the material jetting, so the material may be similar to the previous system, that is a photosensitive polymer resin. So instead of taking it in a vat, so you will be jetting from the nozzles. That's what it is called as a material jetting process. And the third one is a binder jetting process. So where you have a binder here, which is acting as a binding agent between the powder particles. So then you will be jetting the binder from the nozzles. That's what it's called as a binder jetting process. And the last one, the 4th one, which we talked yesterday, is material extrusion process, where the material will be extruded from the nozzle rather than it will be melted, and from the nozzle, so the melted material will be extruding, and you have the material choices. So under this material extrusion, so right from the polymers, metals, ceramics, composites. So these are the 4 3D printing processes we have covered previous lecture. Now today's talk will be on the rest of the 3 processes among this ASTM standardized 3D printing process. Those are sheet lamination, powder bed fusion, and directed energy deposition. So apart from these 3 processes, the scope of the presentation is also a bit of post-processing techniques that are used in these 7 AM processes, and finally the fabrication challenges of the 3D printed parts. So this is what I have planned during this session. So then we'll move on to the sheet lamination process. So what do you mean by a sheet lamination? The name itself is telling you that the raw material may be taken in the form of a sheet, and you will be laminating so those sheets. So what are those sheets? So which you can see here, you have the raw material is in the form of a sheet, either a paper or a composite, or even a metal also nowadays. So I'm going to even talk about some of the metal systems from ultrasonic consolidation. There is a process, and of course So if you see right from the beginning, so I am going to talk the first generation LOM machine, so which along with the SLA, so from Helysis, they have started this process called LOM, that is laminated object manufacturing. The name goes to the Helysis, that is the early manufacturing systems developers from USA, that is Helysis from LOM. And then slowly it has moved to a different approach from the Helysis to the MCAR. It's the Irish technology. So which you are going to use some knife or inkjet printing combinedly, you are going to make the parts in under this MCAR technology. That also we are going to see. And of course, we have a fiber reinforced composites. So that is from impossible objects. So that is also can be covered during this session. And finally, the metals. So how metals can be laminated together. So right from the Helysis system, from the like a paper or a paper like material which is coated a binder or a ceramic. So that is the scope of the previous system called Helysis. From the UC, that is from the metal 3D printing, which we are going to cover these. So then we'll talk about first process, that is the laminated object manufacturing called LOM. So now before going to that, so all of you kindly mute your microphones while logging it into the system.
Please make sure that your mic is muted.
So every time your mic should be muted. Don't switch on your microphone. Kindly note. So then we will talk. We'll see a bit of the working principles of these processes. And let us start with a Helysis system, LOM process, where the raw material is taken in the form of a sheet, and this sheet is coated on top as a material and as the bottom as the binder. So where a laser will be tracing the cross section, rather than there will be a bit contrast process. This one normally what you do by using the laser, you cut the actual cross section, but here it is quite reverse. So we are going to cut, or rather than you are going to cross hatch the system, leaving the cross section alone. So that is a bit different process here. Because of that, you may be wasting a lot of material here. So normally you are claiming that additive manufacturing is 0% scrap, but that statement should be exempted for this technology. Why? Because you are going to have a scrap here more. Why? Because you are cross hatching the object rather than you are depositing the actual cross section. So this is about the Helysis LOM process where they started. And now there is a recent development from MCAR. So MCAR technology, what it do is, so basically it takes a ordinary paper as the raw material. So which we can see the printer looks like this, something like a Xerox machine size, or it resembles like a Xerox machine or a printer, big size printer, or all in one. So here the raw material will be a paper, and then you will be adaptively building, and you have some integrated inkjet printing also to give the colors. So it is the combination of adding or sticking the papers together, and then you will be jetting the ink in the colors. That's what which you can see. All these are in colorful world, it will get you, and it's more or less, it's very no less expensive machine. Why? Because you may be using something like an ordinary paper as a raw material and probably the colored ink. So this is about the technology called MCAR. So if you see the material developments, maybe from paper to now you are able to print a fiber reinforced composites. So the fiber reinforced composites can be possible now with the sheet lamination process, that is with the impossible solutions. So where we can see this is the fiber reinforced composite as printed from this technology. So of course, any technology, it should start with a CAD model, and then you have a fiber sheet to be printed. So then use the inkjet heads to contain wetting fluid, and you will be jetting onto this fiber sheet, and you will be spreading a polymer powder, and which you will be on top of this fiber sheet, and where it will be adhered, and you will be removing the adherent powders, and then where you can see all these bitmap files, so which it got printed. Now you take all the individual sheets, and then you stack together and you put it into the post processing unit, rather than you compress it, and after compressing just you remove the uncoated fibers, and once you remove that uncoated fibers, so then you have left out with a fiber composite. So this is what it works. So that is the development from paper to the uh, composites. Of course, now you can capable of printing in metal also. So it is a bit hybrid process here. So where you will be using even machining also. You will be using a end mill cutter also in between. Say first it starts with welding. By using ultrasonic welding, you are going to join these metal tapes together, and then followed by a end mill cutter will be removing the excess portion or trimming. So you are going to get the advantages of both additive and subtractive here. And basically you are adding these metal tapes together to welding, and removing or finishing will be done with the end mill cutters. So we need to even run the CNC program, generate the CNC program to run the end mill cutting. And of course, so which we can see now, this is going on right now, the welding process of these, and wherever there is an additive, definitely you have a lot of scrap is involved. So which you can see, this is what it's going to build layer by layer with the metal tapes, and finally you have end up with a metal part, which it has started with a CAD model of a digital model of the mold, and now we can see this is the CAD model, and that is the metal die. So these are the developments under this sheet lamination process, and we'll see one by one. So as I mentioned, LOM was the previous technologies where, of course, the carbon dioxide laser used to be the energy source here to cross hatch these sections of the cross sections of the model, which it has derived from the CAD. And during post processing, so just you remove these cross hatched cubes. Normally you call that as a decubing process. You decube those cubes, and the person who is doing post processing must know about the geometry, otherwise erroneously he may cut the actual cross section. So then there will be a challenge for the person who is doing a post processing or decubing process. He must know about the cross section. So this is basically a process, the initial processes, and I am proud to say that I am the person no a person used this machine during my postdoc at US. So right now you cannot find these machines. It got outdated, in fact, but these were the earlier machines. And in India also one or two machines. And Anna University there was a one machine. I don't know right now it is working or not. But LOM is the one of the first among those first generation 3D printers. So then there are a lot of developments, as just now we have discussed. So from the MCAR, where your paper will be the raw material, and by using the inkjet colors, so you could be able to make the different colors. So this is otherwise called as selective deposition lamination called SDL. So where you can make these kind of colored, looking very realistic parts. So this process starts with taking a paper, and then you will be using a printer adhesive, and then you by through inkjet printer you are able to print that ink onto the paper, and then further you will be laminating those papers, and you will be cutting the excess portion through knife, but no laser here. The earlier people used to use a laser, but laser is costly element. Then people realized for cutting paper it doesn't require a laser. Then using a knife is also sufficient to cut the paper. So that's what they realized, and nowadays these machines are very cheap. And XYZ resolution you can get up to 0.1 mm, and definitely you are going to have a photorealistic color, which you can see all these models. You can feel those are a real banana or a real apple or a real orange or a pomegranate. So this is the kind of technology from the MCOR called as a selective deposition lamination. And coming to the ultrasonic AM, so this is nothing but you are taking the raw material metal in the form of tapes, which you can see these are the tapes, and use some ultrasonic welding and CNC contour machining or CNC milling to cut, or it's basically combination of welding and no the milling process. And of course there is another one in the previous video we have discussed, that is a carbon fiber reinforced composites. So these we can make from this technology. So if you see the closer look about the ultrasonic consolidation or ultrasonic welding process, so where you have raw material is this tapes, and those tapes which you can see by using the ultrasonic, as you know the ultrasonic welding is a solid state welding. So then you will be using ultrasonic motion which causes your oxides to break, which we can see you have one layer, you have another layer. So then you will be creating a localized aspirate yield and collapse here, which you can see, and there will be a heat and pressure created, and it will create a high strength in the solid state bonding itself. So that is the advantage of any ultrasonic welding. It's a solid state welding, so which we can get the bonding between the these laminates of metal. So you normally this ultrasonic sonotoroad, so this is which we can see. So there is ultrasonic sonotoroad here, so where it will be joining these metal tapes by using this sonotoroad. And of course it is the combination of welding, and once you do a certain types as a welding and then followed by a contour milling, so that's what your CNC program will come into picture, and it will do contour milling wherever you need finishing, or wherever we need to have some excess portion we need to remove. So then your contour milling will be done. So these are the machines which looks like a CNC machines basically. So that is from Fabrisonic, there is a company. So it looks like a bigger CNC machine. And coming to the applications or the materials or the applications, especially if you see, so I'm getting a lot of questions from the people, know which technology can make FGMs. So one technology it can make FGM is this one. So where we can make a functionally graded laminates. So you can vary the the grading through these laminates. You have that advantage here. So which you can see, and even you have some embedded electronics or sensors. So you can embed here. So you have one more advanced application, that is embedded electronics or sensors is possible through this ultrasonic welding or ultrasonic consolidation. And of course not only FGM, so you can go with the metal matrix composites, MMCs, and which we can see there is a aluminum and you have a titanium laminate. So which it's a combination of titanium and aluminum. Why? Because so you introduce your raw material, these sheets, so one time as aluminum sheet and another time as a titanium sheet, so which it can be laminated together, so aluminum and titanium. And of course you have a alumina fibers can be introduced here, that is through metal matrix composites. So aluminum fiber and the aluminum, so you can make that fiber, what you call the metal matrix composite. And not only that, even you have a silicon carbide fibers can be embedded into your metal laminates. So which you can see the silicon carbide, the fibers got embedded. So these are some of the applications. So I may be very crisp or I may be brief. Why? Because I have to cover other technologies. So then I may be going to the next process. So this is as I already introduced this through video. So you have a kind of a long fiber fabric here, and then you have basically it's a combination of your no fiber thing, and then you have a thermoplastic matrix material, and which you are combining it, and finally you will be stacking it in the laminates form, and you will be putting it into the furnace treatment, or you will be compressing it to get these laminates very stronger and tougher. So this is a typical machine from impossible objects. And if you see closely what is the process under this stacking and bonding of this fiber sheets. So as you start with printing onto the fiber fabrics on it, and then you have you will be using a powder also on that, which we have observed in the previous video, and you will be doing a heat compression of these stacked sheets, and you will be doing it, and then you remove that unbonded area, and then you will be left out with actual components like this. All these are fiber reinforced composites. All these are fiber reinforced composites. So through laminates you are making it. So this is the process about the impossible objects, that is the lamination of your fiber reinforced composites. And that is about the sheet lamination process. And then we will move on to the next kind of process, is a powder bed fusion. So powder bed fusion and binder jetting technology may have some similarities. Why? Because you may take the raw material as a powder in binder jetting also, which we have seen in the last presentation. And here also the raw material is exactly the powder. That's what the name is, a powder bed fusion. So you will be taking the raw material as a powder, and you will be laying like a bed, and then you may use either a laser or an electron beam as a energy source to melt the powder particles or to sinter the powder particles. So you may use a laser, or of course you may use electron beam also. So coming to this powder bed fusion, so the powder bed fusion, so you have, as I already stated, so you have either a laser or an electron beam as an energy source, and you have further SLS was the first technology which was originated from Texas University at Austin. So by filing the patent by the person called Carl Decker. So that was the initial patents along with the FDM and SLA. So at that time, this SLS technology was a bit of indirect method. So means you have to have some binder will be coated on these powder particles. So then once you coated the binder, so then we need to debind it, or basically you're going to get a kind of a green part. But further, in order to make a brown part, and further in order to make the dense part, then we need to use a post processing or a furnace treatment to debind and to sinter. So that was the initial technology under this powder bed, where I'm talking about during early 90s or late 80s. So but now the scenario got changed. So and you have technologies like where now you are able to melt these powders directly. So that's what you can see, the name is slightly changing or moving towards so the earlier the people used to say the SLS, that is selective laser sintering, but now the recent technologies, so that sintering has replaced, or rather than which you can see it is called as a direct metal laser sintering or selective laser melting. So basically you are right now you are not coating the powder with the binder, earlier used to do in a SLS, but now your powders so will be directly it is getting melted through either a laser or electron beam. So that is the development. So anyway, we'll start with the previous technology, or the one of the early technologies under this powder bed is SLS. We'll start with that. So which further even 3D systems has taken over, and of course EOS is another player. So as we know that there was a conflict between these two guys, the patent conflict. Why? Because it looks similar, the SLS, DMLS, it looks very similar. Of course, similar. Only one difference is the binder coating is not there in the direct metal laser sintering or SLM. So directly you can melt the powder rather than indirectly you are melting here in case of SLS. So SLS also you have EOS and you have a 3D systems and you have a sinterit and you have a sintract. And coming to the DMLS or SLM, so where exclusively you're processing metals. So under that you have EOS and you have a 3D systems, SLM, and you have a Renisha. And Concept Laser is a German company, but recently the GE has taken over this Concept Laser. And nowadays you can find a very good number of the companies, or they are no promoting this technology. You have a very good benefits. Of course, these are very costly 3D printing systems also, which recently we purchased one under this is a 3D systems machine, so which is costing around 2 crore. But we can have the metals can be processed, so that is the one advantage, and we can even get very good surface finish. Of course you have other mechanical properties also, but after post processing I'm talking about. So as built you may not compare with the casting, or you may not compare with the forging, but I'm talking about after post processing, after furnace treatment, or after HIP, or after any other the methods which it will improve the mechanical property or microstructural properties or thermal properties or physical property, whatever it is. So after post processing I'm talking about. So and almost similar mechanism we can observe with the electron beam. So only difference between your the electron beam system and SLS or DMLS or SLM is, instead of laser, so you may be using electron beam. But electron beam is having its own advantages, of course disadvantages or limitations, whatever you call. So you have some pros and cons also from the electron beam. So then again, the metal is the material which you are going to use, and Arcam is the company which is promoting this electron beam melting. Then we'll start with the early systems from the 3D systems company, that is called selective laser sintering. So the selective laser sintering, so which we can see here. So the raw material, as we know that the raw material is the powder. So the powder will be taken maybe around 50 to 100 micron size powders will be taken here, and this is the SLS system. So as usual, like we have to start the raw material in a powder form, and then you have to lay a bed. Why? Because it is a powder bed system. So you will be laying the powder, and from the powder you are able to get this kind of it's a polymer parts, so basically or a composite parts, so which we can made from this SLS technology. Predominantly it is polymer, but even it can be composite, can be done. So as usual, like you start with taking the CAD file and you slice the CAD file. So and then after slicing, you send that data to the printer. So in the printer you have a laser, so which the laser and along with the powder bed recoater, and just it will recoat the powder, and then your laser will be sintering your powder particles. By using that laser power you could able to sinter, or you could able to melt the powder particles and getting the bonding between the powder particles, so that it will go layer by layer. So which we can see where the part will be built at the middle, that is the part build chamber, and you have the cartridges, powder cartridges on either side. So while recoating, so the excess powder will be collected on the either side of the bin. So and then you can once you have done all these layers, you can unload the powder through that build chamber, you can take it out, and where you can find something like a cake of powder. So from the cake of powder, so you remove that loose powder and then you can reuse it. And so from the bed of powder, which we can see the actual part which it got sintered. So you have got that part from the after post processing, which you can see. So this kind of parts can be made. So of course after post processing, so then once you after post processing, which you can see, it has enhanced appearance or maybe mechanical properties or microstructural properties or thermal properties or electrical properties, whatever property which you are looking at. So choose the appropriate post processing technique to improve your quality. And then we'll see the second generation machines, that is called direct metal laser sintering or SLM. So in this directly your powder is getting so these are the metal parts which you can see. And again it works with the same principle. You have the material, raw material as a powder, but in this case you are not coated with the binder, but that is a direct metal powder. It is getting melted. So that's what it's called, direct metal laser sintering, or SLM, called selective laser melting. You are selectively melting from the bed of powder. So as per the cross section, so you will be melting. And then anyway you start with the CAD model. Any process, it starts with the CAD model, and like which we have given some demo on the 3D expert yesterday. And similar way, you have one software with individual machines supplier, they will supply. So in which we can see once you slice that model, and then you send that data to the machine. And in the machine where you have these the laser and the recoater. So the recoater will sweep the powder, and your laser will sinter, or rather than melt the powder particles. And where we can see, and it should be there will be a chance of oxides forming. Why? Because you are working with iron. Iron oxide will form titanium oxide. So then there must be an inert gas. So normally in our lab we are using, for reactive materials you must use an argon as a inert gas, and non-reactive materials you can use nitrogen. Nitrogen is bit cheaper than argon. So you're supposed to use any one of these. And once you made this, which you can see, there are the supports. So the supports is also metal. So you have to do a lot of practice here. So then in order to remove the metal supports, maybe from the substrate which you removed, and further we need to use a blasting, sand blasting or air blasting, which we need to do. And if not, it requires some super finishing operations also. And then finally your part is ready for your application. So this is about direct metal laser sintering. And of course, as I already mentioned, so far we are seeing only the laser in action, but you have technology from RCAM, that is EBM, called electron beam melting. So in this, so your same powder, but one more challenge here is, once you are operating with the electron beam, so you must have inner, rather than earlier which you have as an inert gas, but here you need to create a vacuum. So creating a vacuum is challenging, and not only challenging, it's very expensive than than which you work with a laser. So you have a different ball game here once you talk about electron beam. So we need to have a tight vacuum chamber, which as I already mentioned, recently GE has taken over this RCAM company. So why? Because as you know that GE, they are looking for at least making a 50% of their parts through this metal 3D printers. So then which we need to start with the powder, and which we can, as I already mentioned, you have that as a vacuum chamber. So then you have to take the powder, and it should be loaded here, and it should be spread like the recoater, like with the previous system also. The recoating system, there is no difference. You have a recoater which will spread the powder onto the bed. And of course, instead of laser now, so you have a vacuum chamber. Of course, this is the vacuum chamber, and then where everything is under vacuum, and everything now the electrons will come, and so it will melt, or rather than it will, and you may be having a 6 kilowatt beam here, and which can be 100%, no, or otherwise you can have a build speed up to 50% faster. Now you can see the electrons are in action. So where you are, instead of laser, your electron beams, so which you can have a 250 by 430 height, Z height, so which all you see, that is a G component. So that is a blade for a gas turbine engine. So you can make this blade of the gas turbine engine. So then their aim, as I already mentioned, 50 to 6, that's made out of aluminum or titanium. So it can support aluminum, titanium, other metals also. But the challenge here is how to create your, the kind of the vacuum chamber. And once you're done, and of course the post processing, so use remove the loose powder, and you can recycle your loose powder, and you have to be careful while doing it. So then there should not be any metal things, or metallic or magnetic particles, so it will damage, or as you know that electron beam you are using it, so be careful. You do not take such kind of extra care in the laser, but you have to have some extra care towards electron beam, of course we need to. So this is about the electron beam melting process from RCAM, or now it is GE. So this is a setup where we can see you have the raw material, and you have the processing, powder processing station, and post processing station, and of course the 3D printer. So this is about the EBM RCAM technology, where you are using metals processing through electron beams. And of course there is even, I didn't include here, why? Because this is very recent, this is under development, or slightly one or two machines has come out from Valo. Valo is the company, their aim is to eliminate the supports. That's what they are quoting, but I'm not sure how they are going to eliminate the supports. Supports are the biggest challenge for any metal 3D printing, that also we have been facing here. So of course they have a different approach to tackle the support structure, and which we can see these are some of the parts, and this is a sapphire laser they are using here, the Valo 3 sapphire solutions. So like, which we can see, all these are very rugged, and the robust designs of all these machines. And then anyway, any 3D printing system, it has to start with a CAD model, and they are calling it as a intelligent system, or artificial intelligence also incorporated, maybe especially for the support structures, so things like that. So you start with, and of course anyway below 45 degrees it requires supports for any metal 3D printing system. So of course this is a simulation in the software, and which we can see, this is the build volume, maybe around 315 Z height of the build volume, and which we can see this is a turbo machinery. So and this is a hip implant for the biomedical applications. So which these are processed, this high throughput and multi-laser operation they are using it. They are not using a single laser, and of course multi-laser, it will add your the cost of the machine, but these machines are very costly, and they are saying that they are incorporating a closed loop system. You know the advantage of the closed loop system, so we can automatically vary the process parameters, then you can ensure that you have a emulsion pool is maintained properly in such a way that so you can get the better properties. So which you can see, this is so they have automatic powder feeding system or cartridges. So this is basically for the production system, so means not like one part, two part, but daily. So as I already mentioned, like these aerospace people, so they want to make it in a mass, or at least a batch production, which we cannot say mass. Why? Because maybe your aircraft may be in hundreds or thousands, not more than that, but definitely you have a batch production is needed, and then you can use these parts. So this is going to be the future technologies, where we can even overcoming the challenges, whatever the current generation. Now we can say that the third generation machines are coming up now. So as I mentioned, the SLS can, or SLM can process polymers, metals, and ceramics. So anything you bring it in the form of a powder, so which the layer thickness will go 15 to 500 microns, and the powder particle size is 50 to 100 microns. So that is the typical powder. And anyway, we are going to have a exclusively session and followed by my session, and how to make these powders through atomizers or through plasma or any other things, how you can make these and how you are able to achieve these, powder flowability or things like that. And Professor Manjay is going to talk right after my presentation. So you have the parameters, like you have a laser power, of course, the scan speed, layer orientation, hatch distance. These are normally the most affected parameters on the quality of any SLM or SLS system. And these some of the nylon duct for automobile manifolds, and of course you have a titanium bracket for the Airbus application, and EBM is titanium aluminum turbine blade. Just now we have seen from that video the same component, and it is 62 EBM machines are operating by GE. So that is the thing, they have installed 62 machines, EBM machines, across the globe in last year, just 2013, by the GE. And the challenge here is any powder bed system, the health or a safety or a powder recyclation. So you should not inhale the powder, right? So this is order of 50 to 100 micron. So you must have some respirators to keep, or you should not, you have to be careful about these. You have to have some safety precautions. So of course, you have these parts, maybe different companies. UAS is another company. So you may use polymers of like a nylon or a polystyrene or thermoplastic elastomer, or you have other kinds of material, plastic material also. These are some of the case studies from those companies like UAS or 3D Systems or Sinterit. And of course, this is a concept laser, a GE machine. But whatever it is, a GE concept laser or SLM or EOS or 3D Systems or Renisha or any a company, but more or less works with the same principle as we discussed. And of course, the parameters also, like laser power, scan speed, layer orientation, hatch distance, so on and so forth. So we need to nowadays, which we can see, these printers can even print. So see, why I put this slide is intentionally. So 800 by 400 by 500 mm. So means such a huge volume of the part, or the build volume. So, and then you may use 1 kilowatt laser, fiber lasers, two in number. So that is the one. And materials like aluminum, stainless steel, titanium, nickel, cobalt, chrome, copper, and their alloys. So this is a typical material data bank. Now people are in the doing research to add still more materials also under this material bank, and which we can see some of the US and Airbus studies, case studies, where they are making these bigger parts from these machines. And as I mentioned, EBM, this electron beam melting, and of course the same powder will be spread here, and you have an electron beam, and you have a vacuum chamber, and you have a filament. As you know that how to generate an electron, right? You have to have a a filament, tungsten filament normally they use, and you have a grip cup and anode. Just you produce or generate an electron, a stream of electrons, and it will be controlled through this part size. And of course you have a different mechanism. If it is a laser, you have a optic system there, and you may have a magnetic system here. So you have a different work here to compare with the laser based system and the electron beam system. And you have a deflection coil. Of course you have a deflection coil through magnetic thing you are going to operate here. So there in the early system lasers, you may use optic based controller to scan or to control the electron beam and the laser respectively. So you have an electron beam and you have a powder hopper, of course. So, and these are some of the machines. So from Arcam, and these are the parts printed with the Arcam machine, and this is as built. You see, you may not be getting a better quality as built, but after post processing, definitely you can improve your surface finish or the in general the quality of the parts. So Valo, as I mentioned, so they are coming out with the support free laser fusion, and this is the unsupported inner area, and then where you can see some of the parts from and they are saying that this is a no lower angles. As we know that whenever it is 45 and above, only your supports will come into picture as far as metal is concerned. Polymer is a different ball game. So then you have, this is a 10 degree, less than 10 degree, and you have inner diameter is a 40 mm, which you can see there's some other parts. And of course aspect ratio also good nowadays, you can even go 500:1. So but earlier systems was a problem which you cannot make no as height the proportionate, that's aspect ratios are very less in the previous generation machines. But now you have a very good development under this no aspect ratio also. And of course there is a very recent technology which is coming out from the desktop metal, or even you have NXT factory where they may use 4 lasers for this. And desktop metal, they never use any laser. Basically it is a binder jetting and powder bed combination, the desktop metal system. But whatever I have given, this is a different concept from no Aurora Labs. So they have a metal powder and you have a recoating system. They have come out with a different recoating system, a novel recoating tool here. So normally recoating will be done prior to the scanning, but what these guys are claiming, so you can do simultaneously recoating and scanning. So definitely that will save so 50 to 60% or more than that time or build time. This we can expect maybe more quicker than the current generation machines. So you have a multiple layer deposition and fusing in a single pass. And of course they're claiming so it is 55 times faster than the market available machines. So and then even they are saying that so 1.96 kg of titanium per day, so they could be able to print it. So that's what their claim. And print speed may be around 113 kg per day, so maybe targeting to 1000 kg. So of course if you see these figures comparing with the normal welding TIG or MIG, so it may be bit less, but still now people are ready to compete with those speeds also. But as of now these are slow. And in future, and now itself, some futuristic applications, like you have the ceramics. So you have some ceramics printed through SLM or SLS. So you have a direct SLS, so using a silicon carbide ceramics with infiltration. Of course you cannot get directly, definitely it should be done some post processing or some furnace treatment like infiltration. And of course you have a laser melting of sacrificial organic binders is also now is on, which you are going to get a green part, and further you're going to make a ceramics out of it. And then you have SLM is the higher laser energy, so you lower porosity material. And of course these are some of the ceramics that are came out from SLM technology, and which you can see this is a ceramic carbon part by direct SLS, and this is the alumina part from SLA technology. So this is from Canon. So Canon is also now into the business. So and even Xerox company is also now, they have filed the patent recently on 3D printing technology. So and then I will move on to the last technology, that is directed energy deposition. So then what is the difference between the earlier powder bed system and directed energy deposition? So the name suggests earlier you laid the bed, but here no more laying the bed, but you are depositing as for the demand. So means you are directly depositing the powder as required. So means it is something like drop on powder, so that it's not bed of powder, it is drop, demand drop of your powder. Say what do you mean by that? Say you don't lay as a powder, but you deposit from the nozzle these powders. So of course the directed energy deposition, and again you have a two energy sources. One is a laser, another one is electron beam here also. So the laser beam is, say for example, lens is one technology. Nowadays you have several technologies coming up under this directed energy deposition using laser, and one is atomic as I mentioned, and then this is a laser engineered net shaping technology. This is exclusively, predominantly or exclusively metals only it will support. And you have other one is a electron beam additive manufacturing called EBAM from CIACTE. So this is also metal. And let us see the working principles of these. First let us talk about the lens system from Optomac. So what you do here is, as I already mentioned, the powder is coming through the nozzle instead of laying the powder, in contrast with the earlier previous technology which we discussed, that is a powder bed. But here you will be simultaneously, it is something like, looks like welding. So in the welding also, TIG welding or MIG welding, so you will be creating an arc. Here also you are creating an arc, and through high powered laser. So from that high powered laser you create the arc and keep on supplying the powder from the nozzles. So that is the one thing. And now if you see the CIACTE, so the CIACTE is the electron beam source. So instead of laser where the Optomac is using, but CIACTE they are using an electron beam as energy source. So you have to start with the powder as the raw material, and of course the design, and this is the metal part, and which we can see. So of course there's electron beam into action. So you will be simultaneously pumping your powder, and then simultaneously with the electron beam is in action, and then you can able to generate a melt pool or a arc, and then keep on supplying your raw material. So the metal one, now you can see Inconel, titanium, tantalum. So it will support so all these materials, and which you will be feeding these, which we can see this will be fed through the what you call. So you will be pumping the raw material, and as well as your electron beam is also followed by that. And you have a 5-axis systems also nowadays, which you can rotate your table like how your CNC 5-axis CNC machine. And here also you are able to rotate these tables, and you have a 5-axis 5 degrees, and where you can eliminate the support problem, right? So once like how your 5-axis CNC machine will work, and but the accuracy may not be good, which you have seen the previous glimpse, but it's a near net shape we are going to get. And further it should be done with some post processing. So but people like whatever listing here, the Lockheed or GE or Boeing, so all these guys, so they are coming out, or they are using this, adapting these technologies. And of course we have another one is this is a bit wire arc AM, but anyway we have next speaker is going to touch up on this, but just I will give you a glimpse of this wire arc in action. So you can bring the raw material. So far we are discussing the powder, but even it can be a wire, so you can feed the wire. So instead of powder, so you can take the raw material as a wire, but you have challenges once it is a wire. So then but anyway you have to start with the CAD model, as like other 3D printing processes. So you start with the CAD model, and of course you have here as a DMD production unit, or so, which we can see the, yeah, you can see this is a plasma arc welding torch. So and then titanium wire. So basically the metal in the form of a wire, you will be bringing it here, and of course you may be using the high powered lasers to do kind of, or basically it's a plasma, it's a welding technique, like it is very similar to your welding, and which we can see these are the parts made out of this technology. So we will see actually is the session, nice session on this. So I hope I have given a glimpse of this technology. So you have a 5-axis freedom, just now we have seen. So you can have this as a raw material as a powder form here, or it can be what you can see. This is the metal powder is coming up here, and this may be a wire. Just now we have seen like similar to the TIG welding or your TIG welding, and where you can see all these are near net shaped parts, and this is in action. And one more advantage of DED is you can do a repairing and refurbishing. And even somebody was asking, can we use coating? Yes, this is the technology where you can give a coating. Is already you have some machined part, already you have some casted part, already you have forged part. On top of it, you want to apply some other material coated on top of a casted part or a forged part or a machined part even. So this is the right technology for you. So you can use this technology to use a coating. And just now we have seen a video, Siaki, the same guy here, where you can see a wire feeding is here, and you have an electron beam at the center. So, and these are the parts just now we have. And as I mentioned already, there is one more speaker on this. I don't want to step my shoe. I don't want to put it into his thing. Just I'm giving a glimpse of it. And I have a cold spray. That is one more recent say cold spray is as we know that cold spray techniques, which you can have a 45 kg of material per hour. So that is the speed. Otherwise, whatever the previously we have discussed, that may be a typically 9 kg per hour. So you see the e-beam melting process, that may be typically 9 kg only per hour. But now they are targeting it to 45 kg of powder melting per hour. So that is the developments are happening under this technology. And of course, as I mentioned, ceramics is also part of it. Either you can go with the composite matrices like iron, nickel, cobalt, titanium, or a composite ceramics, maybe titanium carbide, tungsten carbide, hydroxyapatite, and you have a carbon nanotubes also possible with this. And apart from that, a pure ceramic like alumina, zirconia, silica, so is possible with this Optomac system. And then let me come to the last part of my presentation. So that is the post-processing techniques in AM. So what kind of a post-processing techniques we are going to use? So under this thing, so we have the post-processing technique is 3D printing technology specific. So we cannot generalize the post-processing technique. Why? Because the raw material is not same for all these processes. So you have a powder as a raw material, one of the systems, and you have just now we have seen as a wire, or it may be the sheet of paper or a sheet of metal, or it may be liquid. So any form, or sometimes you may be atomizing it to get a nanoparticles. So you have different material forms, the raw material forms, so which it is coming up. And at the end of the day, so you got the part. But typically, if you talk about SLS and binder jetting, so your product cost, the 70% of your part cost goes towards post processing. So that is the biggest challenge. So how to minimize this post processing cost, right? So especially SLS, powder jetting, so means powder bed system and binder jetting systems, these are the two. But you talk about other technologies like FDM. So FDM we need not spend. Why? Because anyway you are processing same polymers. So you can either use, say for example, which these are the FDM parts. So you can either use the nose player, or with the hand also you can remove your supports. Why? Because it is a polymer to polymer. But if it is a metal, it is metal to metal, you remember. So then you have these FDM parts. either you remove through a breakaway manual energy, or you have some solvents, so just you can dip it and then automatically it will dissolve, the support will dissolve into that solvent. So you have either cutting or you have dissolving, that's what I'm talking about. You have some dissolvable solvents also, or you can cut it and you have some solvent vapor and you can sand it. So you can sanding and you can do a bead blasting, or you can do a tumbling, or you can coating it on top of the FDM parts, you can even coat. So just don't think that, but definitely FDM parts are not so great for accuracy. So then definitely your application demands to go for the post processing by using any one of these methods, maybe bead blasting, tumbling, or sometimes we need to apply coatings or painting, or depends on your application. And of course, coming to the SLS, so we need to remove from the powder bed and we have to remove the supports too. And we need to have a bead or sandblasting and tumbling, and machining can also be done on this SLA produced parts. So depends what kind of application, and if application demands, so it is not matching your as built parts, so then of course we need to go with the post processing, and you have to invest more also sometimes, depends on application. So then SLA we need to wash it out and we need to post cure. As we understood that every watt photopolymerization process, you will get only 95% of the solid part, but rest will be some kind of a jelly, kind of viscous kind of thing. And every part must undergo a post curing UV bath, it should undergo. And we need to remove the supports and we need to give the coatings. And of course, coming to the jetting technology like a polyjet, we have a dissolvable support. And coming to the binder jet, you have a debinding, that is debinding and sintering. Through that, we can remove these supports. So, and which we can see, this is some of the SLA removed part from the powder bed, and which we can see FDM parts as such on build. This is the thing, but by using some kind of solvent vapor, so they have coated on it, which you can see kind of a glassy kind of a look. So definitely we can enhance the appearance or a mechanical property or a thermal property or electrical property sometimes. So then definitely you must use some kind of post processing technique. So nowadays people are coming out with simplified post processing techniques, of course, and even during the post processing they can even able to apply some colors, or again by using are some barcodes, which you can see, these are the barcodes. So they have printed on top of the 3D printed metals. So parts, say either polymer, basically it's for polymer, that is for FDM process, or even inkjet systems. So FDM and inkjet systems, those parts will be given some kind of lettering or some kind of scan barcodes or whatnot. Even some kind of electronics can also be possible to do a kind of and of course we have some automated post processing techniques in EAM. So for the FDM, for removing the support and surface finishing. And of course SLS part, which we can see, this is a metal part here, there is a support here, and this is as built. But this is as built and this is after post processing, which we can see even during the post processing in the furnace treatment, which your color also got changed, means you might have enhanced some properties. Definitely this is as built, and of course some appearance area value also it might have improved from as built to the surface finishing. And of course you have some exclusively, some companies they are working on post processing services exclusively on post processing, so they won't make any machines, but they have some post processing machines. So it may have some hybrid systems also. You may have two perpendicular or a single axis just jet streams, so which right now there is, it's going on some kind of compressed air, and then some use some kind of a detergents and suspended solids, and which provided getting some targeted blast. So then you have a post processing machines exclusively to do this, and of course you have a service providers also to do this job. And then why we want to go with the post processing, as we know that as built you cannot, whatever I have already answered some questions from the participants saying that it may be on par with casting or it may be on par with forging, but that is subjected to the post processing, after post processing. So you have some then why you want to post process, and what are the limitations? You see other side of the coin, the 3D printing. So you have an anisotropic properties, and we have to have a lot of list to discuss, but at least what we can do, so in order to improve a corrosion resistance or oxidation resistance, or we need to go with surface friction or a kind of a wear, improving these properties I'm talking about. And we need to improve tensile strength sometime, so we need to improve bending fatigue, and we need to improve some kind of apply some kind of adhesions on cellular adhesions or biofilms or appearances with some other. So it depends on application. So where that part will go, if it is a simple nut and bolt, so you need not much worry about the other aspects, but you may be worry about some aspects. But if it is flying in an aircraft, so altogether it's a different story. So you have to have special measures and special certification it needed, or it should be given a kind of a qualification by the Federal Aviation Authority or the concerned authorities has to certify it, or it has to qualify. Until unless you cannot use them as for that purpose. But simple like a nut and bolt, no, it doesn't require any certification, or it doesn't require any qualification. Why? Because it's not a critical application where you're using it. So depends, like if it is a critical application, of course we need to go. And why? Because it is directly related to the cost of the component. So then what are the methods that you can do under the super finishing of the AM parts? And of course, as usual, whatever the conventional machining or casting or forging route, normally you may use these. And similarly, you may use a sanding, polishing, machining also you can do. And you have a vibratory grinding, and you have a abrasive flow machining, and you have a short peening or a blasting, and you have a chemical etching is another process, and electro polishing can be done, and you have a vapor smoothing, and you have a electro deposition, dyeing, and you have a spray coating or a dip coating and whatnot. You have several methods, so that can be applicable here in AM in order to improve or in order to get super finished part. So which there are some novel approaches in enhancing the surface finish or super finish. So you have under that you have a dry electro polishing, so which we can see there is a RA value which is less than 0.1, but normally as built it may typically you may get around say 10 to 15 RA value, or at max you may get 7 RA value. That is a maximum you can get it out of as far my knowledge goes in this scenario. But my 10 or 15 RA value has improved to 0.1 RA value. So through this dry electro polishing or a laser polishing from Fraunhofer. So this is as built a knee implant. So that is say 7 micron RA value. Now after a laser polishing, so it is 0.1 microns. Depends, like say your application demands, say where you need to have the strength or any other biological what you call ASIO integration purpose. Why? Because it's a biomedical application rather than it is an implant, so which is made out of a cobalt chromium. So definitely as for the surgeon or as for the doctor's requirement, so definitely you can enhance. So or not only a cobalt chrome, here is another implant that is a titanium spinal implant, this one. And this is also again through this novel kind of a super finishing process, you could able to even reduce your RA value from 10 to 15 to 0.1 0.1 RA value. So we can achieve in that way. And you have a complex geometries and micro scratch free and resolved geometry, and then reproducibility. And of course we need to have this selectively and micro scratch free components, you can get it, and you have a very fast particle free and reproductivity and surface densification. And of course surface densification, anyway my next slide probably will talk about that. So you have the surface smoothing, of course, as so this is one of the FDM fabricated part. It is an RF horn antenna for an aerospace application. So where we can see by using some solvent vapor mix, and this is a very smoothened, and because of that, which you can see the performance. So they basically this antenna, so this RF antenna. So after using this super finishing operation, so where we can say the enhancement in the functionality or the surface smoothing in the antenna, and because of that your performance got improved. So that is another advantage. It is just not like appearance of purpose, but it is enhancing the performance of the system through this super finishing operations. And last one is, so how to achieve 100% dense? So that is the challenge. So but no doubt nowadays these almost all AM except one or two under powder bed or DED as built, you can achieve 95% dense. The old days are gone, but now the third generation machines can achieve 95% dense. But still, if you want to have 100%, of course we need to have 100%, your application demands, and then go with the hipping, that is hot hydrostatic pressing. So you can use a hip process, so where we can see some entrapped powder or some cracks may not be no it is there. This is before the hip, so which we can nowadays you have a monitoring in situ monitoring systems. Even you can take the image of each layer, and then you have the systems, and there is a huge potential to develop or do research or develop your own system, how to have a closed loop controller to achieve this. But my knowledge goes a very limited machines are giving with the high-end machines these kind of provisions, but you cannot get these provisions for a typical machines which even you spend 2 crores of rupees or 3 crores of rupees. So you are not nowadays getting, but maybe in future definitely there will be a scope to find that kind of machines or that kind of provisions or that kind of features can be incorporated with the standard basic machines also in the future, not now. So you have this, as you know, that hip process, you know how a hip process. So the hip, so it is something like putting in a cooker, pressure cooker, right? So what, so you keep it the so after whistles also, some 3 whistles or 2 whistles, so you will be keeping the rice cooker is on, right? So then similar way, which you have some hipping process here, and you may have here the pressure, it may go up to 5800 or 30,000 psi, and it may be going up to 2000 degrees C. So that is the typical hipping process which you may use, and then this hipping process will achieve 100% theoretically the maximum density, and which eliminate microstructural porosity, and which removes the printing defects, of course, just now which we have some defects, and which it can be cooked together, or it can be merged, or it can be it can remove the printing defects, and will remove the micro cracks also, and which it will ultimately, it may improve the ductility, fatigue, and resistance to critical high performance materials. So but the challenges are there still, and you have a defect elimination without coursing the microstructure. So that is the challenge here. But anyway, nevertheless, you have a provision, so you can do it. So and let me conclude my presentation with this slide. So what are the fabrication challenges that the current AM is facing? So let me put it in this way. So the challenges are many. Why? Because the first challenge is standardization of the process. Say I don't have, first of all, ASTM standards to standardize my thing. So So, and then if at all, if I want to standardize, so from machine to machine, it is getting deviated, or you have a different mechanism or physics altogether. So you cannot generalize these things to a, why? Because machine to machine it will vary, and even run to run, the consistency may not be same. So then there is a challenge. So how to standardize these processes? Why? Because you are getting the deviation from run to run on the same machine, or machine to machine, of course, or technology to technology, model to model. So that is the challenge. So, and then of course there there will be a problem with the source of material or the raw material also. So then consistency, say you have a powder, right? So the powder is, which we are saying that 50 to 100, there is a range, right? So during that range, so then how do you ensure that, no, that you are going to have an average particle size maybe in between? So are you able to get it that? So that is the challenge. So the raw material itself, are you able to get the consistent properties, the once you characterize your powder, so are you able to get it or not? So, and then you have a post processing requirements also, like where uh, the process controller and the error correction is also another area where we need to have work on it. And of course post processing requirements, like you have, we have already discussed, like some of the systems, 70% of the cost of the part is going towards post processing. So then it is impacting your cost, and of course time. So post processing times, it will take, even you have to include this time also in the post, while calculating your, no, coming out with the project time and the project completion time. So we need to have even the time, and of course the quality is also. And as I mentioned, the certification of the parts, this is a major no challenge. Know how to distinguish a good part and bad part if you are not having a certification. So definitely it is a challenging one. So how can you ensure that if you are having some standard ASTM so and so number, and this is what got certified, so absolutely fine. So you can compare if you have some reference or a standard, but unfortunately you don't have a certification of these parts. And you have a new potential, no health hazardous to operators. And of course, especially if you work with a powder bed system or any powder, there will be a chance of inhaling, or there can be a volatile organic component called VOCs or some fumes. So by chance you may inhale those fumes or those particles. So then we have to have a safety measures, or so you have to have some respirators to put, so to know, especially the people who is directly working with the powder systems. So that is another challenge which we need to. And integrity of digital data. So then now this is a digital data. Now you have done some exercises also right now on Thingiverse or on a GrabCAD. So now the data, the designs are open in the web or in the internet. But how to secure your designs? So definitely in the future, uh, we are not going to buy the machine. Very soon we are going to buy the designs. Why? Because in my home I can have my printer, but in India we don't have much awareness about this 3D printing technology. But if you see in US, at least 25 to 30% of the household people using these 3D printers at their homes. So then we need to sell the designs but not the machines in the future. So as of now it may be happen for the polymers, but it may be the case very soon for the metals, composites, or ceramics. So that is going to be, so we are, if that is the case, so anybody can download or anybody can, tamper your designs. So then there must be some blockchain technology to secure your data. So this is the biggest challenge is under industry 4.0. So then we need to take care about this, the kind of data which it should be secured. Of course, some service providers like, cubic chain technologies, or even GE is also developing their own blockchain technology to protect their designs. from the hacking or from tampering these designs, right? So that is another challenge, the biggest challenge under this industry 4.0, right? And of course, the finally you have the protection of IP, that is say your patent or your IPs. So the protection of IP. Why? Because no, I don't want to name some guys, but like people may replicate or no, they may duplicate or they may copy the technologies. So that is the biggest challenge for the how to protect your IP. So these IPs are different than the conventional IPs. Why? Because why I'm quoting, then people has to rewrite their legal procedures. Why? Because so you are able to buy a machine, or you are able to fabricate your own machine, and you are keeping at your home, and what you are printing, who knows, right? So then anyway you have to your legal laws should be rewritten. So as we know that 3D printing, it is a disruptive technology, not only disrupting the manufacturing or any other technology, it is disrupting the what you call the policies. So your legal lawyer, or you go to IP related some lawyer, so then it is a challenge for him how to protect. Why? Because your 3D printers are at your home, right? So if it is at a common place and somebody knows that you are downloaded something and you are printing it, say if I am having a printer in my home, I have a design of some gun, something like that, say then who is going to stop me? So then I can fabricate, then I can use it for some illegal activities. So nobody will stop us. Why? Because I have a drawing somewhere else I downloaded, or somewhere else I have taken. So anyway, so just you can have a thought on it. So then everything, your 3D printing is rewriting all policies also in that sake. Okay, so then I will stop my presentation. I am on time, so I have stopped my presentation here, and then I will hand over to the Narayan Reddy.
So thank you, Ravi Kumar sir. It's a very nice presentation regarding to the printing of composites and ceramics. Uh, so, dear past participants, if you have any questions, please ask the sir, or you can post in the chat box.
Good morning, Ravi sir. This was a good presentation, indeed, actually. And I am attracted towards the direct energy deposition process, which is similar to our welding. Can I say that is it a alternative technique as means an advancement of conventional welding?
Yeah, you can say in some aspects, definitely it is superior than a conventional welding in some aspects. For example, heat affected zone. So you have high heat affected zone in welding, conventional welding, but here you have almost negligible heat affected zone if you compare with, relatively I'm talking about the welding, conventional welding. So that is the one positive sign, but the other negative part of it, we have to talk on both sides. But the speed may not be as speed as the conventional welding, like a TIG welding, or it is not that much speed. So but definitely there are a lot of improvements is coming up. So I am not going to say it is going to replace, but definitely we can see some good amount of advancements may happen. So whatever, wherever you have some kind of a limitations or constraints, if you challenges, if you call over the conventional, very soon it's going to overcome. Yes, so definitely you have a specific advantages or specific applications which otherwise you cannot do, or with compromisation you may using through welding technique. So definitely you can come to the DED if that is the situation. DED technology will help. Yes, you are absolutely correct. Yes.
Okay, sir, another one, if it is a sheet metal laminating fabrication process, what is the limitation of sheet metal thickness? Is it any limitation for the
Uh,
sheet?
yeah, that again, that is another challenge. So maybe it may be half inch or quarter inch.
Okay,
So
okay,
that is the
okay,
order of the day now. So maybe that
okay,
is the slowing down the. That's what I'm talking about. Say the speed maybe still it may be less if you compare with, but it can be improved. But you have some challenges to increase. Maybe half inch is also, but there will be a lot of challenges. But it is not. We cannot go 1 inch or 2 inch or 3 inch or 4 inch like that. No.
okay,
but but ultrasonic consolidation may be bit, but it is also not that order 1 inch or 2 inch or so. Still
okay,
that limitation is there. Yeah.
okay, sir. Thank you, thank you.
Next.
So then no more questions. Then you do have any chat box question, Narayana?
Yes, sir. The one
Can you?
question from Kanchi Sai Prasad, he is asking, sir,
Mhm.
could you please tell me from SLS or SLM, which one will be suitable as which one is suitable aspects for medical applications like scaffolds, etc.
Um, say both are good, but SLS will not the direct process which we are going to get the metal parts. So that depends on what kind of material you are looking at. Are you looking at for the implant material is a metal, then go with SLM. But if your implant material is a polymer by a FDA approved or a medical grade polymer you are looking at, go for the SLS. I hope I have answered your question. Next. Do you have any chat box question, Narayana? Still?
So in composite AM,
Mhm.
is there any method to have continuous fiber as we have in conventional method?
Yeah, so then probably you might have seen one of the processes which it may be taking, but some extent it may be true, but it is not like conventional which you will be doing it. But still there is a gap between conventional methods and here. Hopefully maybe in future it can be bridge the gap between your conventional filament or whatever the composite continuous fibers. So it's going to be very soon we can see such kind of a thing. But as of now, it is no. Answer is no as of now. Yes. Next, Narayana.
I'll ask. Sir.
Sir, one more question.
Mhm.
Uh, why supports in SLM? It's a powder-based technology. He's asking like,
Mhm.
why do we need a supports in SLM?
Mhm.
Miss
Of
Richa
course.
Agarwal.
Yes, yes. Very good question. What is his name?
Richa Agarwal, ma'am.
Richa Agrawal. Madam, very good question. You asked. I think you are very keenly following the processes. Yeah, I appreciate your question. Though it is a powder bed system, normally people will have the opinion that if it is a powder based system, so loose powder will act as a support. Probably that is your concern. And of course, you have a very good observation, madam. I appreciate for your question. So yeah, but the thing here is, yeah, okay, madam, very good question. But in the reality, if it is a polymer, you don't have a much challenge to the basic concept here as a support for the metal I am talking about. For the metal, it is very tedious. The kind of the internal stresses which it is going to create while melting or while your laser is scanning, and your support is also acting as a conductive material supports. And normal assumption people will say that eliminate the support, but elimination of the supports is not thumb rule, rather than it is not sin, right? So it is other way around. So it is acting as a good conductor. So my answer is for your question. So it must consist of the support. The support is somewhat, it is eliminating your internal stresses which is developed inside, and it is acting as a conductive kind of a stuff for some extent at that layer, so to minimize such kind of thing. Otherwise you may have a big problem of warpage or things like that, and then we need to spend much of the time or much of the money towards setting that error, rather than if you are removing the support at that position. So you may pay very expensively on this kind of a post processing, or sometimes build failure may happen. So in order to avoid that, so it is better to have a support for the SLM. So I hope I have answered your question. So that is the
Thank you,
basic.
sir. Thank you. Thank you, sir.